Every year, the world produces over 390 million metric tons of plastic, according to 2021 global statistics from sources like the OECD. This enormous volume underscores the massive scale of plastic manufacturing and the growing challenge of managing the resulting waste. Sadly, much of this plastic ends up as persistent waste, overwhelming vast landfills and polluting our oceans, where items like bags, bottles, and microplastics drift through currents, endangering marine ecosystems for generations. But what exactly happens to plastic after we throw it away and it leaves our homes? Today, we follow its journey step by step into a real, operational recycling factory to uncover the truth behind the process. Here inside the facility, the transformation begins with heavy industrial machinery in action, gears smoothly turning, conveyor belts rumbling powerfully, all captured in slow motion amid volumetric God rays piercing the dust-filled air. At its core, plastic is a remarkably durable synthetic polymer material derived primarily from petroleum, formed by linking countless monomers into long, strong molecular chains that give it exceptional longevity. In stark contrast to organic waste, which breaks down rapidly through microbial decomposition in a time-lapse fashion, plastic resists natural degradation and can endure in the environment for hundreds of years, making effective recycling absolutely vital. That's where specialized recycling factories come in, employing precise mechanical methods to dismantle the plastic, convert it into reusable forms like flakes for new products, significantly cutting down on landfill accumulation and preserving scarce petroleum resources. Closed-loop recycling can save up to 70% of the energy required for virgin plastic production. The recycling journey starts on expansive tipping floors up to 10,000 square feet, where heavy-duty trucks deliver massive loads, typically 20 to 30 tons of compressed plastic waste bales, and unload them in a dusty cascade. Conveyor belts then activate, transporting the mixed plastic waste at speeds of 1 to 2 meters per second into the heart of the plant, enveloped in the constant hum of machinery, rising steam, and swirling dust particles illuminated by factory lights. Sorting stands out as a critical initial step, ensuring that contaminants are removed and plastics are separated by type for optimal downstream processing efficiency. Workers stationed on elevated platforms, clad in full safety gear including helmets and gloves, meticulously pick out non-plastic contaminants like metal cans or glass shards from the rapidly moving conveyor stream with precise, practiced movements. Automation follows with sophisticated optical sorters, such as Tomra auto-sort machines, which deploy near-infrared spectroscopy at 900 to 1,700 nanometers to identify plastic resins by their distinct molecular signatures in real time. This technology separates PET bottles, density 1.38 grams per cubic centimeter, from HDP jugs at 0.95 grams per cubic centimeter, operating at high speeds exceeding 2 meters per second up to 4 meters, while air jets pressurized to 0.5 megapascals accurately deflect the flakes into dedicated collection chutes, achieving up to 95% purity. Moving to shredding, powerful granulators like Cumberland single-shaft shredders, featuring 100 to 200 rotating steel blades spinning at 300 to 500 revolutions per minute, aggressively tear the sorted plastics into uniform flakes measuring 10 to 12 millimeters wide, handling 5 to 10 tons per hour with intense mechanical force. By shredding the plastic into these small, consistent flakes, the process vastly increases the material's surface area, which is essential for more effective cleaning, decontamination, and uniform melting in the stages ahead. The flakes now plunge into enormous hot water tanks filled with detergents, a 1 to 2% sodium hydroxide solution heated to 80 to 95 degrees Celsius, where they are agitated for 10 to 20 minutes, effectively dissolving adhesives and allowing labels to detach and float away. Intensifying the cleaning, friction washers with high-speed rotating drums at 1,000 to 1,500 revolutions per minute vigorously tumble the flakes, combining mechanical scrubbing action with high-pressure water sprays to remove ingrained dirt, oils, and residues, often followed by float sink separation tanks based on density differences. After washing, centrifugal dryers spinning at 2,000 revolutions per minute or air classifiers reduce moisture content to under 1 to 2%, The clean, dry flakes are then extruded in twin-screw machines like Arima or Coperion at 240 to 260 degrees Celsius for PET or 200 to 250 for HDP, with vacuum degassing to eliminate volatiles. Filtered via 50 to 100 micron screens, and cut by underwater pelletizers into 3 to 4 millimeter pellets at rates of 100 to 300 kilograms per hour per line. Rigorous final quality controls, including inline near-infrared spectroscopy, intrinsic viscosity tests targeting 0.60 to 0.80 deciliters per gram for PET, and checks ensuring contamination below 50 parts per million plus moisture under 0.02%. Guarantee the pellets meet standards before packaging in 25 to 50 kilogram bags for reuse. Through this intricate, multi-stage process, everyday plastic waste is reborn as premium pellets destined for new bottles, containers, and products, exemplified by facilities like Carbon Light processing 100 million pounds of PET yearly or Veolia plants worldwide. While in the US, 5.7 billion pounds of PET bottles were recycled in 2022. Reclaiming 28% of sales volume and promoting a sustainable closed-loop economy.
After the initial sorting and thorough washing stages, the plastic flakes still retain considerable moisture on their surfaces, which must be meticulously and completely removed before advancing to the subsequent stages of the recycling process. This critical dehydration step plays a vital role in safeguarding the quality and structural integrity of the recycled material, preventing potential issues down the line. Centrifugal drying machines vigorously spin the plastic flakes at high speeds, harnessing powerful centrifugal force to effectively shed and separate water droplets from the material. Following this, hot air drying systems activate, circulating streams of precisely heated air through the flakes to evaporate any remaining moisture, ensuring they are bone dry and ready for melting. Achieving complete moisture removal is absolutely paramount because even trace amounts of water can severely compromise the high-temperature melting process ahead, causing issues like steam formation or material inconsistencies that lead to defects in the final recycled plastic products. Once the plastic flakes have been thoroughly dried to an optimal state, they stand ready for the transformative next phase. They are steadily fed into a massive industrial extruder, recognized as the powerhouse heart of the melting and reshaping operations in plastic recycling. Within the extruder, the plastic progresses methodically through multiple heating zones, each one set to progressively higher temperatures than the last. This carefully controlled temperature escalation guarantees uniform melting of the plastic without any risk of overheating or degrading the polymer chains. Powering this process is a robust rotating screw that relentlessly pushes the plastic forward through the heating zones, compacting it tightly while promoting even heat distribution throughout the mass. This mechanical precision is crucial for generating a consistent, homogeneous melt essential for quality output. As it travels deeper into the extruder, the solid plastic flakes begin to soften and ultimately transform into a thick, viscous molten liquid, flowing like a glowing, river-like stream of material. This fully molten state is indispensable for the precise reshaping that follows in the recycling chain. Transitioning seamlessly, the molten plastic now enters the pelletizing stage, where it is forced through a die and then expertly sliced by rotating blades into small, uniform pellets. These pellets become the standardized, versatile raw material feedstock for producing new plastic goods across industries. Right after being cut, the still scalding hot pellets are immediately channeled into an efficient water cooling system. This rapid immersion in cool water solidifies them instantly, averting any clumping or deformation and readying them perfectly for storage and shipment. These compact, uniform pellets represent the culmination of the recycling effort, serving as the premium raw material poised for delivery to manufacturers. They will be molded into an extensive variety of new plastic products, thereby completing one full cycle in the recycling loop. Running parallel throughout the entire recycling sequence are rigorous quality control protocols, featuring automated inspection systems that scrutinize the pellets for precise size, uniformity, and color consistency. These checks confirm adherence to exacting industry specifications vital for downstream applications. Complementing this are sophisticated contamination detection systems that scan for and excise any foreign particles, impurities, or deviant materials overlooked in prior steps. Such vigilant measures preserve the pristine purity demanded of high-grade recycled plastic. Materials deemed unfit by these rigorous evaluations are methodically rejected by the automated machinery without hesitation. This safeguards the supply chain from substandard product, ensuring only top-tier recycled plastic proceeds to manufacturing. Nevertheless, despite these advanced techniques, a sobering fact remains. Not every plastic item is suitable for recycling via this pathway. Factors like diverse polymer types and stubborn contamination levels frequently limit what facilities can effectively reclaim and process. Consequently, rejected plastics regrettably are routed to landfills or incinerators as a last resort. This reality spotlights the genuine constraints of today's recycling infrastructure and technologies, urging ongoing advancements. Yet for those plastics that navigate this gauntlet successfully, the payoff is pristine pellets primed for reinvention into fresh items like sturdy bottles, durable containers, and reliable pipes. This rebirth underscores recycling's tangible impact. This elaborate process exemplifies human innovation in waste reduction and resource recovery, compelling us to reflect on our shared duty to refine these methods further. Embracing such progress fosters a sustainable harmony with materials for generations ahead.